In this lesson, we'll be addressing the question of how do you justify and use the formula for the circumference of a circle. If you recall, pi is a mathematical constant where pi is approximately equal to 3.14159. Pi is also irrational, which means that basically you can't express it as a fraction for any numbers, a or b. So basically what that means is pi does not equal a over b for any integers a and b. Also, the decimal expansions of pi does not terminate and never repeats. The reason why pi is in the introduction of this lesson is because you're going to be seeing it a lot throughout the lesson. Okay, so here it is, the circumference of a circle formula. So the circumference c of a circle, if you remember, the circumference is the distance around the circle. Okay, if I wanted to find the circumference of a circle with radius r, it's given by this formula. C equals 2 times pi times r, where c denotes the circumference of the circle and r represents the radius. Now, we could take the formula for what it is, but it's valuable to know where this formula comes from. So in order to do that, we're going to attempt to justify the circumference formula. Now here's our plan. What we're going to do is, to find the circumference of this circle, we're going to put regular polygons and inscribe them inside a circle. Okay? As the number of sides of the polygons increase, the perimeter of the polygons get closer to the circumference of the circle. And you can see that here. Here is a regular pentagon. Okay? And if we then inscribe a regular hexagon, followed by a regular octagon, and then follow that by a regular nonagon, you see how as our polygon that's inscribed has more and more sides, the perimeter of the polygon gets closer and closer to the actual circumference of the circle. So we're going to use that as a key part of our argument. Now suppose we have a circle and we're going to call it O. Typically when you name a circle, you name it after the point that's at its center. Okay, so the center is also named O. And the radius is r. So here's the point O, the center of the circle, after which the circle is named, and here is the radius r. Okay. What we're going to do is we're going to inscribe a regular N-Gon. What I mean when I say regular N-Gon is I'm going to put some arbitrary regular polygon on the inside of this circle. Inscribe it like this. It's called inscribing a polygon inside a circle. Okay, so I'm going to assume that this N-Gon, the reason I say N-Gon is because I'm not assuming that this polygon on the inside has any certain number of sides. I'm just saying it arbitrarily has n amount of sides. Okay, so what we're going to do is inscribe this regular N-Gon in the circle O, and we're going to draw the radii. Radii is plural for radius. Okay, so we're going to draw these radii in here. Okay, we're going to draw these radii in to the vertices of our arbitrary N-Gon. So suppose this length right here, AB, is one of the sides of our inscribed polygon, and then we're going to draw this line segment OM from O to the midpoint of AB. That's extremely important. This point M here is the midpoint of AB. Notice that this triangle AOM is congruent to triangle BOM by the side-side-side congruence criterion that you're already familiar with. Why? Because notice that this length here of the triangle AOM is congruent to this length here of this triangle, because these are both radii of a circle. And for any given circle, the radius has one distance and not more than one. Also, notice that this side here of this triangle is congruent to this side of this smaller triangle. Why is that? Because remember, we said that this point M, we were drawing it so that it's the midpoint of the segment AB. Right? So these two triangles, I now know that they have at least two things in common. They have this side in common, this side in common here, and also this side is in common with this side. And notice by the reflexive property of congruence that this segment OM is congruent to itself. Therefore, these two triangles have three sides in common, so by the side-side-side congruence criterion, these two triangles here are congruent. Since these two triangles are congruent, I also know that angle 1 is congruent to angle 2 because they're corresponding parts of congruent triangles. Now, notice that there are going to be exactly n number of these triangles, and they're all going to be congruent to triangle AOB. Why do I say there's n of them? Because you can imagine there are exactly n sides to this polygon that we've inscribed. Therefore, there are exactly n of these triangles that sort of fill up the N-Gon. So what we can say is that the measure of angle OAB, so this angle here, okay, the sum of 1 and 2, has to be 360 degrees divided by n, the number of sides in the polygon. Why do I say that? Well, because if you remember, all of these angles inside this polygon should be 360 degrees. Okay? But if they're all congruent to each other, all of these triangles here, so here's one triangle, AOB, here's another one here. Okay, this traces out another triangle, and another one would be here. All these triangles are congruent, and if we're looking at this angle here to find the measure of it, it's just going to be 360 degrees divided by the number of sides on my polygon. Okay. Since that's the case, and I know that these two small triangles, AOM, is congruent to MOB, I know that triangle 1, or angle 1 is congruent to angle 2 because they're corresponding parts of congruent triangles. But that just means that if this angle here measures 360 degrees divided by n, then each one of these have to be exactly half that measure. So if I take this expression, cut it in half, I get that the measure of angle 1, which is the same as the measure of angle 2, equals 180 degrees divided by n. Now, since angle OMA is congruent to OMB by CPCTC, and OMA and OMB are also a linear pair, that means that these angles are supplementary and must have measures of 90 degrees. So both of these triangles, AOM and BOM, are right triangles. Now if you look at triangle AOM, the sine of angle 1, if you remember from SOHCAHTOA, the sine of angle 1 is opposite over hypotenuse. So the sine of angle 1 would be the ratio x over r. Notice that I can solve this equation here, the sine of angle 1 is x over r. I can solve that for x by multiplying both sides by r, and that gives me that x equals r times the sine of angle 1. But we already know the measure of angle 1 in terms of n. It's 180 degrees divided by n. So now we have an expression for x that involves r and n. Now what we're going to do is express the perimeter of the N-Gon. Remember, perimeter means distance around, so we're looking for an expression for the perimeter of this polygon here in terms of x. Notice that the length of this side here, AB, is twice x, because m is the midpoint of AB. This means that the perimeter of the N-Gon, since there are n sides and this length AB is twice x, then there has to be 2x times n as the perimeter of this polygon, which is the same thing as 2 times n times x. Recall also the formula for x that we derived earlier, that x equals r times the sine of 180 degrees over n. If we substitute this, we get our expression for the perimeter of the N-Gon, so it now becomes 2 times nr times the sine of 180 degrees divided by n. Now, our expression for the perimeter of the N-Gon includes this expression here as a factor. If we use a calculator as follows, we can investigate what happens to the value of this expression as n gets larger and larger. So this is how we do it using the calculator. So I'm interested in what happens to this expression here as n, or x in this case, gets larger. Well, this is what you do. You enter the expression, this expression here, as y1 into your graphing calculator. You go to the table setup menu and enter the values that are shown below here in the table setup menu. Then you can view a table for the function. And you can use the arrow keys to scroll down and see what happens as x gets bigger and bigger and bigger. You look at the value of y1, which is just the value of our expression here. And you'll notice that as n gets larger and larger, the value of this factor gets closer and closer to pi. So as n gets larger, the expression for the perimeter of the N-Gon approaches 2 times pi times r. Remember to come prepared to class with answers to these reflection questions. Here we're going to show an example of how the circumference formula is actually used. So suppose we had to find the circumference of this circle O, and we wanted to round to the nearest tenth. First thing we need to do is find the radius, because the formula for circumference involves the radius. So the diameter is twice the radius in all circles, so in this case they're giving us the diameter of this circle, but I'm only interested in the radius because the formula for circumference involves the radius. So I take 12 meters divided by 2, and that gives me a radius of 6 meters. And then I just use the formula directly. The circumference of a circle is equal to 2 times pi times the radius of the circle. But I already know the radius is 6 meters, so I plug that in for r. And using a calculator, I get that the circumference of this circle is approximately 37.7 meters, since we're rounding to the nearest tenth. Alright, so now let's solve another circumference problem. The General Sherman tree in Sequoia National Park, California is considered the world's largest tree. It's approximately circular at its base with a circumference of 102.6 feet. What's the approximate diameter of the tree? And we're going to round to the nearest foot. Okay. So since I know the circumference of this tree, I'm going to substitute 102.6 for c in the formula for the circumference of the circle. Okay, just like this. Once I have that, the variable that I'm interested in is finding the diameter, but first I need to find the radius, so I divide both sides by 2 pi and get this expression for r. And then I just use a calculator to evaluate this expression here, and I end up getting approximately 16.329 feet. But you have to remember that we're interested in the diameter of the tree, which is exactly twice the radius, so the diameter of the tree is approximately 33 feet. So here's a question that we addressed in our lesson today. It's, how do you justify and use the formula for the circumference of a circle? Well, to justify the formula, if you remember, we basically inscribe a series of regular N-Gons in a circle of radius r, and the perimeter of each N-Gon is 2nr times the sine of 180 degrees divided by n. As n gets larger and larger and larger, the expression gets closer and closer to 2 pi r. Now, in order to use the formula circumference equals 2 times pi times the radius, first thing you want to do is find the radius of the circle and substitute this value for r into your formula. And use a calculator to evaluate this resulting expression, and then you can round and you'll have your circumference. So to summarize in your notebook, write a journal entry in which you summarize the main steps in the argument that justifies the formula for the circumference of a circle, and remember to include at least one figure in your journal entry.